Hello and welcome to our averages project. The Pythagoreans distinguished 10 different averages. We will consider 2 of those averages that are still used today, or at least should be. The average quantity is the sum of the quantities divided by their number, so x bar is the sum of the x's over n, where x are the quantities and n is the number. So if I asked you for the average quantity of 0.5 and 1.5, you'd add them up, that would give you 2. There's 2 of them, so you'd divide by 2 and that would give you 1. Now that works fine for things that you can add up, but now let's ask a different question. Suppose that you want to find the average rate. So let's start with an investment of $1,000. That's not going to be important later on, but it's a nice way to start. In the first year, the value of the investment went down by 50%, and in the second year, the value increased by 50%. Now, it would be very easy to imagine that this ends up back where it started from, up 50%, down 50%. But that assumes that this behaves like addition, but rates behave like multiplication. And you can convince yourself of that pretty easily. If you decrease by 50%, you only have half as much. And so when you increase by 50%, that 50% is only of the 50% that was left. So you're only increasing by 25%, not the 50% that you'd need to get back to where you were. So let's work through the arithmetic and see why that's true. So it says that in the first year, the investment lost 50%. Let's show that as a decimal. So if you go down 50%, let's represent that as a negative, and let's convert that percentage into a decimal. So negative 50% becomes negative 0.5. So the growth multiplier is what we multiply by to get the result that we're interested in. So I don't multiply by negative 0.5 if I go down by 50%. That tells me how much I've lost. I'm interested in what remains. So the growth multiplier m is 1 plus r. So for that first year, the year in which the value of the investment went down 50%, we say that m1, the growth multiplier of the first year, is 1 plus negative 0.5. Well, that ends up with 0.5. That makes perfect sense when you think about it. If it goes down by 50%, only 50% is left. Only that half that you didn't lose is left. In the second year, the growth multiplier is m sub 2. It's 1 plus 50%. So 1 plus 0.5 is 1.5. And so now we know that we take the starting investment of $1,000 and we multiply it by both of these multipliers. So when we do that, that just is a matter of doing some arithmetic. We've already done the addition inside of parentheses, but let's show it again. 1 minus a half is a half, 1 plus a half is 1.5, and then we do the multiplication. Now think about it. We're basically going down by a half, that's giving us $500, and then we're only going up by 50% of that $500. Well, 50% of $500 is $250, so from that low of $500, we're only going up to $750. Now notice that this is very different than what we got when we computed the arithmetic mean for the average quantity. Then we got back to 1. Whatever we started with, one thing undid the other. The average, in terms of the arithmetic mean, of 0.5 and 1.5 is 1, 100% to what you started from. But that's not true for an average rate. Let's look at the second example. It asks us to find the average growth multiplier for the account from example number 1. So now we know that we ended up at the end of 2 years with $750. We started with $1,000. So let's go back to that same equation and let's plug it in. So the key idea here is we want to find the growth multiplier that would have yielded the same result had we earned that rate both years. Let's introduce some new notation. M for multiplier, we've been using that, but M bar for the kind of average multiplier. So we're saying that A is 1,000 times M bar times M bar. In other words, what rates it would have had to have changed in both years to end up with that $750. So of course the first thing we need to do is realize that we ended up with $750. So in the place of A, the number that we found in the previous example, we've got 750. We started with that 1,000, and then we want to know what constant growth multiplier would have made that 1,000 into 750 in 2 years. So m bar times m bar is m bar squared. Now we're going to use arithmetic to find what m bar is. So as we work backwards through the order of operations, we're going to try to get m bar by itself. So the order of operations say to square and then multiply. We're working backwards. So we're going to undo the multiplication first, dividing both sides by 1,000. 750 divided by 1,000 is 3/4, 3 over 4. And now, of course, we need to undo the square, so we're going to take the square root of both sides. So here we are taking the square root of both sides. Now that'll give us m bar by itself. The square root of 3/4, well, division inside of a radical can come outside, so that leaves us with the square root of 3 over the square root of 4. The square root of 4 is, of course, 2, so that leaves us the square root of 3 over 2, and we put that into a calculator and round it to 4 decimal places. Now we know what growth multiplier would have resulted in a change from $1,000 to $750 in 2 years. Now we want to ask the question, well, what percentage would that be? So when we turn the page, the next thing that we're interested in is to use the definition of the growth multiplier, in other words, how it's related to a rate R, to find the average rate at which the account in example 1 changed. So we're still talking about that $1,000 that went down by 50% and then up by 50%. So let's start with that relationship between the growth multiplier and the rate, and then let's plug in what we found in the previous example, namely that the growth multiplier is 0.8660. And then let's solve this for R. To get the R by itself, we need to undo that addition. Addition is undone with subtraction. We're going to subtract 1 from both sides. So on the new right side, we're taking that 0.8661, we're subtracting 1, and no great surprise, we're getting a negative. That means that it is falling, and hopefully that makes perfect sense to you. We started with $1,000 and we ended up with only $750, so clearly it is falling. Let's say this in words. This says that the value of the count fell, so that's taking the place of the negative sign, that's telling us that this rate is negative, by 13.4% per year on average. And that on average means that that 13.4 is what it would have had to fall by each year so that it fell by the same amount. Now let's look at some more generic questions where we're just given some growth multipliers. So in example 4, we've got M1 is 1.3, M2 is 0.2, M3 is 1.5. And we want to find the average growth multiplier for those 3 years. So we're going to do exactly what we did before. We want something m bar that behaves like those 3, but is the same. In other words, if I multiplied m bar times m bar times m bar, that was 3 times, it would be the same as multiplying each of these individual growth multipliers together. So on the left side, we're saying that we're interested in a growth multiplier that when you multiply it by itself 3 times, behaves like m1 times m2 times m3. Now I've got a little bit of arithmetic to do here, so we went off to the side, 1.3 times 0.2 times 1.5, press enter, and out came 0.39. So now we want to get the m bar by itself. We need to undo the cube, and of course we do that by taking the cube root of both sides. Now on the left side, the cube and the cube root undo each other. We don't have to worry about signs because the index and the exponent are both odd. And we're interested in finding a growth multiplier anyway. On the right side, we've got a little bit of arithmetic to do. If finding the cube root key in your calculator is a pain, you can always use the fractional exponents and rewrite this as 0.39 raised to the 1/3 power. That might be easier in a modern calculator. And when you do that, you get that the growth multiplier, the average growth multiplier, is 0.7306. So that was 3 years. Let's take a look at example 5. In example 5, we're interested in 4 years. So we're going to go through this just a tad quicker because the arithmetic and the algebra is the same. We're now looking for a growth multiplier that behaves like those 4 individual multipliers. So we want an m bar to the 4th that is the same as m1 times m2 times m3 times m4. When you do that arithmetic, you get 0.21. We then need to get the m bar by itself, which means that we need to take the 4th root of both sides. Don't worry about the signs. We're interested in a positive anyway, so the fact that if m bar had been negative, it would have become positive is not an issue for us. So we can simply say that that preserves equality. We put that into our calculator. Again, if finding the root key in your calculator is a pain, you can always simply raise it to that reciprocal power. So of course the reciprocal of 4 is 1/4. 1/4 is 0.25. So you can write this as 0.21 raised to the 0.25 power. And of course you'll get what I got, that m bar is 0.6769. So example 6 is a very similar question, except we don't have to worry about the arithmetic for it. We're just given 5 growth multipliers, m1, m2, m3, m4, and m5. So we're going to do exactly what we did with the arithmetic, but now entirely with variables. So because we're interested in a growth multiplier for 5 years, we're going to raise m bar to the 5th power, and we're going to set that equal to the product of those m's. And just like before, to get the m bar by itself, we have to take the 5th root of both sides. So that gives us the 5th root of m bar to the 5th. That's going to undo each other, the 5th root and the 5th power, leaving us with m bar. On the right, we just have the 5th root of the product of those 5 growth multipliers. And nice answer, the 5th root of m1 times m2 times m3 times m4 times m5. Now we want to generalize this to n years, and in a sense this is even easier than the previous example, because now we're talking about raising m bar to the nth power and setting it equal to the product of m1 through mn. We're going to then take the nth root of both sides. On the left side, the nth power and the nth root are going to undo each other, and we're just left with m bar being the nth root of the product of n things. We're basically using the nth root to treat those m factors as if they were the same. That's very similar to what we're doing when we add up n things and then divide by n. We're imagining that all of those n things were the same. And if you add a number to itself n times, you get whatever that number is, x times n, and then you'd undo that times n by dividing by n. So this is basically the exact same procedure, just the operations are increased by 1 order. So instead of adding up the m's, we're multiplying the m's. Instead of dividing, we're taking the square root. Remember, division undoes multiplication. The square root undoes exponentiation. So there's our formula for the geometric mean, the average rate.